Thank you, Professor Marija Orlović. Dear colleagues, dear students and professors, my name is Marija Orlović and I will present to you my master thesis named The Occurrence of Icing Raindrops on Power Lines. First of all, I want to tell you what was my mentor's inspiration for this master thesis. Well, a few years ago, Majdanpek was hit by a heavy ice storm and that caused huge damage. Many houses were left without electricity, and our minister Aleksandar Antić visited that place, and while he was reporting for the local news, a big icicle fell down and hit his head. Fortunately, he had a helmet and nothing happened to him, but that helmet had been broken, and today it is stayed in Ministry of Mining and Energy here in Belgrade. As I mentioned, the occurrence of icing raindrops may cause many damages, especially if ice is formed on transmission lines of electric power network. These disasters can be collapse of load-bearing structures, transmission lines and poles. And this occurrence is often appeared in North countries such as the United States, Japan, Canada, Russia and so on. There are two ways of forming ice load on hanging power lines. First case is due to the freezing rain, and second case is if the temperature of rain droplets is above freezing point and they contact solid surface which temperature is below freezing point. So let me explain what freezing rain is. Well, in high layer of the atmosphere, due to the low temperatures, snowflakes are formed, and due to the gravity, they fall down. They have to pass through a layer of atmosphere where temperature is above freezing point, and then snow melts to rain. And after that raindrops pass again through layer where temperature is below freezing point, and they can never become flakes anymore. So that rain droplets becomes super cooled, and they freeze when they contact solid surface, which temperature can be above and below freezing point. So the goal of this master thesis was to consider and analyze this icing process, and for that purpose horizontal cylinder is observed. It has zero heat capacity and thermal conductivity, and that cylinder is exposed to vertically falling rain droplets. Temperature of rain droplets is above freezing point, and air temperature is below freezing point. If a drop or air temperature is sufficiently high, freezing may not begin on the upper half of the cylinder, and that film water flows along the cylinder and cools due to the convective heat loss to cold air, and freezing may begin at some location. It is necessary to determine the mass balance equation and heat balance equations separately for upper and lower halves of the cylinder, because impinging drops have influence only on the upper half of the cylinder. So the mass balance equation for the upper half of the cylinder is determined by equation 1, and by the integration of this equation it is obtained that mass flux of water flowing along the cylinder depends on rainfall rate, cylinder radius, and angle measured from the top of the cylinder. Also, it was necessary to determine heat balance equation. It is assumed that there is no radial temperature gradient inside the water film. Kinetic energy of water and air are neglected. Also, heat released by evaporation and heat released by runback water are also neglected. So heat balance equation for the upper half of the cylinder is given by equation 3, and it states that the rate of change of water's internal energy depends on convective heat loss to the air and sensible heat of warm droplets. Equation 4 is heat balance equation for the upper half of the cylinder where angle is 0, and it is used for purpose of obtaining the dimensionless form of this equation 3. Also using dimensionless surface temperature given by equation 5, dimensionless form of the equation 3 is obtained and it is given by equation 6, where A is parameter and the angle has values between 0 and half of pi. Equation 6 is first-order linear differential equation, which can be solved by Fourier's method of separation and has only one analytical solution for A equal 1. And equation 7 states that dimensionless surface temperature depends only on angle measured from the top of the cylinder. This procedure is also applied for the lower half of the cylinder, and equation 9 represents distribution of dimensionless surface temperature for the lower half of the cylinder, and angle theta has values between half pi and pi. This graphic represents the dimensionless surface film temperature around the cylinder for different values of parameter A from 0.01 to 20, and for high values of this parameter, correspond to rapid heat exchange to cold air or to a small mass flux of film water flowing along the cylinder. So it was also necessary to determine location where freezing begins, and that location is obtained from condition that heat loss to the air is in balance with sensible heat secured by warm droplets. And the location where freezing begins is given by critical freezing angle, equation 11, where alpha is heat ratio parameter. And the mass of ice is also determined from condition that that mass is equal to the difference between the convective heat flux from the cylinder and sensible heat flux of warm droplets. A thickness of the ice layer is given by equation 14, and this thickness actually represents difference between radius of ice cylinder and the radius of non-ice cylinder, and it is obtained from condition that volume of ice per length meter is equal to the surface of the ice accretion, which is perpendicular to the cylinder axis. And it can be concluded that this occurrence of icing raindrops may cause many damages, such as overloading, collapse of load-bearing structures, damaged power cables and towers. And these processes are more often appeared in Serbia. And the mass of ice formed on hanging transmission lines has no influence on the distribution of electricity, just on increasing cable weight, which may lead to many disasters. Thank you for your attention.